Hello, so we are continuing on from the previous video and we are doing this validation check. So firstly we want to enter things which should be accepted by the system, which is a 1 and a 0. So if I enter a 1, it accepts it because it moves on to the next statement. If I enter a 0, it also accepts it because it moves on to the next statement. Now we want to check invalid entries, so -9 and some random symbol. So if I enter -9, it doesn't accept it, that's good. And it says please enter 1 or 0, error has occurred. Wonderful. And if I enter the @ symbol, so there we go, please enter 1 or 0. Wonderful. So those checks also work. And they work for both Dijkstra on a directed graph and Bellman-Ford. Now the reason why I don't need to do the same thing, so the reason why I don't need to check it on Bellman-Ford as well is because of how the system is created. It takes it to the same subroutine anyways. And you can see that in the technical solution side of things, in the code itself. So doing the test on Dijkstra on a directed graph is sufficient to say it will also work on Bellman-Ford. Okay, now we need to actually test the optimization itself. So we want to test Dijkstra on a directed graph. So we want to check that for graph C inputted, the correct shortest path, distance and alternative paths are shown, and our start and end nodes are A and D. So let's have a look at graph C. Oh, my bad, that seems a bit stuck. I will fix that in a minute. Graph C looks like this. You can just about see it. No, you can't. You can't see that bottom one, can you? Oh, that's annoying. Sorry, really wasn't planning on this happening in the middle of a video. Wonderful. Now you can just about see it. So, our start and end nodes were A and D. So let's input graph C into the system. So if I just return to the main menu, this is Dijkstra on a directed graph. We have 4 nodes, and edge AB has a weight of 2, edge AC has a weight of 5, AD has a weight of 3, BC has a weight of 0, BD has a weight of 1, CD has a weight of 7. Our start node is A, our end node is D. Is there a path from A to B? Well, let's look at the arrows. A to B, yes there is. So we put a 1. Is there a path from A to C? Yes there is. Is there a path from A to D? Yes there is. Is there a path from B to A? Well, the arrow only goes one way, so no there isn't. B to D, yes there is. C to A, no there isn't. C to D, no there isn't. D to A, no there isn't. D to B, no there isn't. And D to C, yes there is. And this is what our result tab shows us. So it shows us, that the shortest distance is 3. Is that what we were expecting? Yes. The shortest path is ABD or AD. So path of AD, alternative shortest path ABD. So it works on that graph. That's good to know because that shows that the optimization has performed its role successfully. Now we need to make sure that, as with Dijkstra on an undirected graph, Dijkstra on a directed graph can also handle graphs which haven't got direct connections. So we're going to use graph B for this, and we're going to have start and end nodes A and C, and we should have this correct statement. So, and I'm also going to do the test like I did with Dijkstra on an undirected graph from A to B, because that also, it would also be useful seeing how it reacts then. So 5, 0, 0, A to C first. Oh, yeah, wonderful. Is there a path from A to B? Yes. Is there a path from B to A? We'll just say yes. And we found the path isn't reachable, no such path was found. So that's good. And if we quickly check it on A to B, we should get a path. I know this isn't in the testing table, but it's worth just having a look. So yes, good, we get a path. So that's good. So we can tick that off. Right, then we'll move on to A star. How long do we have? We've only been 5 minutes. Okay. So now with A star, if I go here, A star works on a coordinated grid, right? So each node needs to have its own coordinates. And these coordinates need to be positive whole numbers, and we need to check that. So we want to check that the coordinates are positive rational numbers, not whole, sorry, positive rational. So the first test is inputting of 5, and we should have that the input is accepted. So if I go here, A star, so let's just enter 7 nodes. So actually no, because then we're going to ask for the weight of each edge. Let's enter 4 nodes, and let's just do 1, 2, 3, 4, 5, 6. Start node, doesn't matter. So if we enter a 5, it works because it moves on to the next stage of entering the y coordinate of the end node. Now test number 18 is 5.75, just to check it works on decimals as well. Wonderful. Then if we have a look, test number 19, entering a 0. So this is one of our extreme values. So that works, which is good. Then it's entering a -9 and coordinate. So things that aren't acceptable, and we should have that our input is rejected. So if I enter a -9, please enter a positive y coordinate. If I enter coordinates, please enter a valid y coordinate. Wonderful. So those tests work with our coordinates. So we can pass them, and we can pass them here, and we can pass here and here. And how long do we have? We have 3 minutes. So now we want to test that the optimization A star itself actually works. I'm going to do this in a new video because I don't think I can quickly do it in 2 minutes remaining. If I just quickly explain what test 21 does. So now we're using graph D. So this is what graph D looks like, and you can see that each node has been given a set of coordinates, and we want to have our start and end nodes being A and D, and we should have the correct shortest path, distance and alternative paths shown. So we will do that in the next video.